Welcome everyone to another TCS Plus talk. Today it's a great pleasure to have Zamir from Tel Aviv University, who's going to be talking to us about his recent stock paper on the optimality of frequency moment estimation. And now, before we get started, I do want to say a few words about TCS Plus. So TCS Plus is an online seminar we've been running now for very many years, and we have a very nice online archive of talks. We're always looking for more suggestions. So there's in our website, if there's a paper that you think is really cool or would make a very nice TCS Plus talk, please give us suggestions and we can try to include it either in this semester or in the subsequent semester. Um, that being said, I guess the we'll have this talk is being recorded, and there'll be maybe a short 15-minute unrecorded session toward the end where we can ask or more questions or have subsequent discussion. But other than that, I'll turn it over to Or, and yeah, please take it away.
Sure, thanks Eric, and thanks everyone for showing up. Good, whatever time it is, wherever you all might be. I will indeed talk about frequency moments. This is a joint work with Mark Braverman, and you should all feel extremely free to stop me for questions at any point during the talk as well. You don't have to wait until the end. And also let me apologize in advance if I'm going a few minutes after time. Okay, so let's begin by describing the model in which we are going to work. So we're going to work in something called the streaming model. I'm sure many of you have encountered it, but even if not, it is the following not that complicated thing. So usually we have the input to our problem. It is all given to us at once. Then we want to compute something on it and return that as an output. In the streaming model, the input is partitioned into a stream of smaller elements. So now we're not getting all of the input at once, but we are getting those elements one by one. At the end, we will want to say something about all of the stream that we have seen. But now our measure of complexity is not going to be the amount of time we are spending, but how much memory, how much space we needed whenever we saw those elements one by one. Could we do it with much less memory than just remember everything and computing the answer at the end? So the space we need will never be more than n, the length of the stream, times, I don't know, log n or whatever is the size of a single element's representation. The question is going to be for which problems we can do with much less memory than this. And we're going to discuss a meta problem or a family of problem called frequency moments estimation. So let's define it as well. So for a single element in my universe, some element that I might see in the stream, we are going to define its frequency to be how many times it appeared in the stream. So the frequency of x is how many times I saw x. And now the k frequency moment, and k can even be not an integer, but at first we will think of integers, is just the sum over all elements in my universe of the frequency of the element to the power k. So this is just the sum over different elements of how many times I saw it to the power of k. So let's look at this quantity for a second, and for some small values of k, ask ourselves, what is this thing? What are we seeing here? So what is, for example, the first moment, f1, we're going to call it. So this will just be the sum over all elements of how many times I've seen each element. This is just the length of the stream. What is going to be the zeroth moment? Let's say that I define 0 to the power of 0 as 0, but anything else to the power of 0 as 1. So the zeroth moment, when I put k equals 0, is now going to count how many distinct elements I have seen. Because regardless of what was the frequency of an element, as long as it was not 0, I counted it one time, and otherwise I didn't count it as well. So this now seems as maybe something that is more useful than just the length of the stream. But it turns out that even though in many places you might want to know how many different things you have seen in a stream, it makes more sense to look not at the zeroth moment for many applications, but on the second moment. So what exactly is the second moment? The second moment is something that we sometimes call the collision probability. This is the same up to normalization as the probability that if I take two random indices in my stream, that I see the same element in those two indices in the stream. So this is also sometimes called the repeat rate, or as I said, collision probability. This is in some sense a more robust version of how many different elements I have seen in my stream. So the distinct elements, they wouldn't care if I have seen an element once and everything else 1,000 times. The second moment will be slightly more robust. It will not be as affected by one thing that I have seen. It will be affected by how many different things I've seen at more or less the same amount of times during my stream. Okay, good. And the problem that we are going to try solving is given a stream and given a specific k, we want to return at the end an estimation of the k frequency moment. What do I mean by an estimation? We want with good probability, say better than 0.9, to return something that is between 1 minus epsilon times the actual quantity, fk, to 1 plus epsilon times this quantity. And everything I've said so far, the formal definition of the streaming model, this meta problem of a frequency moment estimation, and also the algorithm we will soon see to compute the second moment of a stream, all of them were introduced in the same seminal paper from 30 years ago, more or less, of Noga Alon, Yossi Matias, and Mario Szegedy. And let me just, in a couple of sentences, say that this work of theirs is considered extremely influential in both theory and practice, because we have a rare occasion here in which we have a model that is quite clean, theoretically. I mean, we didn't say anything that looks too crazy, but it is very useful for many applications in real life, in which we see very large streams of data and we don't want to remember everything, but we want to be able to say something about the stream. So this is very useful in databases and in network analysis and so on. And even for this work, the three of them won the Gödel Prize. So just to maybe try to convince you that this problem is important for whatever reasons. Okay. And for the remainder of this talk, we are going to mostly focus on the second moment. And maybe one reason at least to convince ourselves that in the second moment something interesting already needs to happen is that it seems like when we see an element, we need to know something about how many times it appeared before to be able to compute the second moment. Because for example, if we see an element for the first time, then its contribution to the second moment is just going to be 1. But if this element appeared many times before, then its contribution to the second moment is going to be much more than 1. So a priori, it seems like we might need to actually remember everything we have seen so far to say something in the end about the second moment. Or do we, right? Would probably not be here if we truly needed to remember everything. So what we are going to see next is the AMS algorithm, the algorithm from this paper of Alon, Matias, and Szegedy, that shows how we can estimate the second moment of a stream with much, much less memory than remembering the entire stream. And the algorithm, and this maybe is another reason this was also so influential in practice, the algorithm is extremely elegant and simple. Also very clever. It is not clear at first sight why it works, but it is just a couple of rows. It is really an extremely elegant thing. So this is the entire algorithm. We are starting by drawing a random function from our universe of elements 2 plus and minus 1 uniformly. Let's for now not discuss how exactly do we maintain this thing in memory, how exactly do we represent in memory this fully random function, but let's say that we have this random function for now. Now we are going to initialize a counter s to 0. And now whenever I see another element in my stream, whenever I see some element xi, I'm going to update my counter by either +1 or -1. According to what? According to the value of this random function mu in the element that I am seeing. So I'm just adding mu of xi to this counter that I maintain in memory. And in the end, I'm going to return this counter square, which is something non-negative. This is it. This is the entire algorithm, this few rows, more or less. First of all, how much memory did we need to do that? So I only have a counter. If I forget about the function, I only have a counter in memory. This counter represents an integer between minus n and n. I only need log n bits to remember the value of this counter. So I really didn't use a lot of memory, much, much less than n or n log n. But what did I compute? What is s squared? What did I return? So one thing to notice is that let's look at the extreme cases. If, for example, all of the elements in my stream were the same element, now the frequency moment, the second frequency moment should be n squared, right? I have one element with frequency n, then f2 is n squared. Then what I see in S at the end of this algorithm is just either plus n or minus n, because I added the same thing n times. And then S squared will be n squared, exactly the F2. Let's look at the other extreme. If every element appeared only once, now I want the frequency moment to be n, right? F2 is n because the frequency of every element is just one. Then what am I seeing here? So what I have in my algorithm now is just a random walk, an unbiased random walk, right? Because every time I either add one or add minus one with the same probability. So S at the end is going to be something like square root n, and S squared is going to look something like n. So not exactly, but something like what should be the second moment. So it turns out that this thing is true in general, that the expectation of this counter squared is always going to be exactly the second frequency moment. And why is that? Because what is S squared? This is just the sum over all pairs of indices of this function mu at xi times this function mu at xj. And by linearity of expectation, it is enough to just ask ourselves what is the expectation of this product for two particular indices. But what is that? If in those two indices I see the same element, so mu returns the same thing, then mu of xi squared is always going to be 1, right? Because it is either 1 times 1 or minus 1 times minus 1. So for a pair of indices that are pointing towards the same element, this expectation of this product is 1. But what happens if they are different elements? Then mu of xi and mu of xj are independent, and each of them is uniform over plus minus 1, so the expectation of each of them is 0. So the expectation of this product is 0. And this means that I am actually counting how many pairs of indices are the same element. So at least the expectation of S squared is exactly what I want it to be. It is exactly the second mode. But is this good enough? Are we done? So now we have this estimator that in expectation is exactly what we want. This is not truly enough, right? Why is this not truly enough? Because we might have a lot of variance. So I'm not going to do the calculation of the variance, but doing something very, very similar to what we had on the last slide, we can also see that the variance, we just need to calculate the expectation of S to the power of 4 now to be able to calculate it, is something like the second moment square. Not very surprising, but also not great, because this means that the standard deviation is going to be of the same order of magnitude as the result I want to output. It's going to be of the same order of magnitude as the F2. So what can I do to lower this variance? What can I do to lower the standard deviation by a factor of epsilon to get a 1 plus minus epsilon approximation? So the standard thing to do when I have this random process and the expectation is good, the variance is not amazing, and I want to lower the variance, is to just do it many times independently. But I see the stream only once, so I will do them in parallel. Okay, so what do I mean by that? What do I mean by that is that if I want to reduce the variance by a factor of 1 over epsilon squared, it is just enough to run the same algorithm in parallel independently 1 over epsilon squared times. This would reduce the variance by epsilon squared and the deviation by a factor of epsilon. So the real algorithm is still just those 3 lines, but now each line happens a few times in parallel. So I don't have only one random function, I have 1 over epsilon squared random functions, and not one counter, but also that many counters. In the end, each of those counters I'm squaring, and I take the average of all of them. And now the variance is small enough. So now this average will, with good probability, be a 1 plus minus epsilon approximation of the second moment. Okay, and what was the one point that I lied about, that I swept under the rug? How much memory do we need for, okay, first of all, for the counters, then here nothing changed. We just have this log n we had before times the number of counters. This is a log n over epsilon squared. But the one thing that I didn't tell you how to do is how do we also remember those functions, those random functions in memory. But here we just need to make one small extra observation, which is that we didn't need those functions to be fully uniformly random. It was enough for them to be four-wise independent. For the expectation calculation, we only needed them to be two-wise independent. We only looked at pairs of variables. For the variance, you would also need to look at four tuples of elements. This is why it needed to be four-wise independent. But we know that we can draw and represent such functions in memory using only log n bits. For example, by looking at degree 4 polynomials or something. Good, so this doesn't add to our memory more than the how much we already paid for the counter. So in total, we still need only log n over epsilon squared to remember all of those copies at the same time. Good, and this is it. This is the algorithm. And the main question we want to answer in this talk is, can we do better? Is this log n over epsilon squared optimal or not? What is already known? So focusing on those spatial cases we mentioned before already of k equals 0, 1, and 2, what was already known? So for the cases of k equals 0 and 1, of distinct elements and approximate counting, actually we know the exact needed space complexity for a while now. So approximate counting, this doesn't even care about what is in the string. This is just about can I maintain a counter approximately with less memory than I need for simply counting. For this, we have very classical solutions and lower bounds. We know that you need something like log n bits of memory for that. For the distinct elements problem, we also know for a while now that the amount of memory we need is log n plus 1 over epsilon squared. So there is something that is better than this algorithm for the second moment that I have just showed you. But the lower bounds here, the lower bound of the log n plus 1 over epsilon squared, it actually holds for any moment, not even only integer one, besides approximate counting. Which means in particular that the very same lower bound also holds for the second moment, also holds for the collision probability. So we have the same lower bound also for the second moment, and the best upper bound we had for the second moment was what we have just seen, this log n over epsilon squared, which is slightly unfortunate because there is a gap between those things that can get up to quadratic for certain parameters. So for example, if epsilon is 1 over square root log n, then the upper bound is log squared of n, but the lower bound is just log n. And so it's not even nearly tight in some sense. Why am I focusing only on moments that are at most 2? Why is the case of k equals 3 not as interesting or useful and so on? So it is not that it is not interesting, it is still interesting, and a lot of work was dedicated for analyzing those cases as well. And for all of them, by now we have nearly tight bounds up to logarithmic factors. But the unfortunate thing about moments larger than 2 that we know for a long time now is that the minute k grows larger than 2, we actually need polynomial space in n. So we can no longer solve this in polylogarithmic space. So those are not as useful because they're not as efficient anymore. And also the lower bounds are slightly easier because now we don't care about logarithmic factors anymore. Because now they will be of lower order terms. They're not the high order terms anymore. Logarithmic factors because the main term is now going to be polynomial in n. Okay, so what are we showing? So in essence, we are showing that the AMS algorithm is tight. It is the best that we can do, but not exactly. So let me add two footnotes and why they are there. So what we are showing is that for every epsilon that is at least 1 over square root n, we need at least log of epsilon squared n over epsilon squared bits of space to get a 1 plus minus epsilon approximation of the second moment. So the first point, this is actually fine, like asking epsilon to be larger than 1 over square root n. This is actually necessary. Why is this necessary? Because otherwise there is a better upper bound, right? Otherwise we can just remember the entire stream. I would never need to pay more than n or n log n or something like this to just remember the entire input. So I can't expect 1 over epsilon squared to remain the correct bound when epsilon is smaller than 1 over square root n. So this part is fine. But the second question is, why did I replace the n within the logarithm with epsilon squared n? Or does it even matter? So when does it matter? If epsilon is slightly larger, is polynomially larger than 1 over square root n, then it doesn't matter at all. Right? If epsilon is larger by a polynomial than 1 over square root n, then log of epsilon squared n is the same up to a constant as log n. So this actually shows that in that entire range, AMS is optimal, which we previously knew only for a constant epsilon. So this is good. But when epsilon is very close to 1 over square root n, then this log might get smaller. This might now be less than log n. And we were actually quite surprised to find out that the problem was not with the lower bound, but with the upper bound. So we're actually showing a better algorithm in this very particular range of very small epsilon, showing that the lower bound is the correct thing. So we end up with showing that this is the exact space complexity we need for this problem in this range of epsilons. Okay, good. And I will just mention very, very briefly that if you care about non-integer moments, then actually this lower bound also extends to the range between 1 and 2, which was the only range in which we didn't have tight or nearly tight bounds before. So now we have tight or nearly tight space bounds for a moment estimation for any k. Okay, so what is the plan for the rest of the talk? The plan is to say something about our previous lower bounds achieved. What are the tools that are used to get those streaming lower bounds? Then what went wrong with getting a tight lower bound for F2? And finally, we will give some high-level details of what did we do to break out of those barriers from before. What did we do differently? Okay, so the main tool, already starting from the AMS paper to get lower bounds for those streaming problems, was using lower bounds from communication complexity. What is communication complexity? So it is the standard drawing. We have two players, let's call them Alice and Bob, as usual. Each of them is getting their own input. Let's call them in this example X and Y. And they want to compute a function of both of them inputs, both of their inputs. So they want to compute some function of X and Y. And I don't care about how much space each of them uses, and I don't care about how much time each of them uses. The only thing we are going to care about is how much do they need to communicate to each other to come up with this output, with the function of both of their inputs. So they are allowed to talk, and now the complexity is going to be how many bits of communication did they need to send to each other to be able to compute f of x and y. And actually for the rest of this talk, it suffices to even look at the simpler model of one-way communication complexity, meaning that Bob is not allowed to speak at all, only Alice is allowed to speak. She sees her own input, she can say something to Bob, and then seeing this message and his own input, Bob needs to come up with the output. So Alice can always just say X, say her entire input. The question is, when can she say less? For some problems, it suffices for Alice to say much less than her input for Bob to be able to come up with an answer. For other problems, she needs to say more or less the entire input she has. And because of how restrictive this model appears to be, for a very long time now, we know how to get lower bounds for communication complexity, which makes this a very good starting point for lower bounds in other regimes. Whenever we can reduce some communication problem to another model, this is a good way to get lower bounds in the other model as well. Okay, so indeed, what we are going to do is to take a communication problem and reduce it into a streaming problem, meaning that if I have a streaming algorithm that doesn't use a lot of memory, for some reason this will result in a communication protocol that doesn't send a lot of communication. And then lower bounds for the communication problem would translate to space lower bound for the streaming problem. So the general recipe is going to look like something like this. I will take my stream, my stream of n elements for the streaming problem, and I would partition it between the two communication players, between Alice and Bob. So for example, the first half of the stream might be some encoding of Alice's input, and the second half of the stream would be some encoding of Bob's input. And we would do it in such a way such that if we construct this stream with the first half constructed by Alice and the second half constructed by Bob and run the streaming algorithm on it, then the answer returned by the streaming algorithm, we want this to imply the answer to the communication problem. So we want the result for the problem that the streaming algorithm is solving to imply what should have been the answer to the communication problem for this type of reduction to work. And now how would the reduction look like? So the reduction would simply look as maybe makes sense. So Alice has her own input in the communication settings, meaning that she can simulate the first half of the stream. She can create her own half of the stream. This is just an encoding of her input. And if she can create this half of the stream, she can also run the streaming algorithm on that half of the stream. So she would just create this half of the stream, run the streaming algorithm on it. And then when she reaches the middle of the stream, she can no longer continue running the streaming algorithm. Why? Because she doesn't have the rest of the stream. The rest of the stream is an encoding of Bob's input. So what would she do? She would want to somehow wrap up her own work and tell Bob, okay, this is your business now. You need to continue running the streaming algorithm on the input that you can construct. But what does she need to send to Bob for Bob to be able to continue running the streaming algorithm? Just the state, the memory of the streaming algorithm at this point. Because if she would send the entire memory of the streaming algorithm to Bob, then Bob can just continue running the streaming algorithm from this point on, because Bob has the rest of the inputs. So what would be the communication that Alice would need to send to Bob? Simply the space used by the streaming algorithm in one single location. So this is just the space used by the algorithm. And now Bob can start from this point, pick up, finish the run of the streaming algorithm with his half of the stream, get the result of the streaming algorithm, and from that, as we said, this should imply the answer to the communication problem. So now Bob can just tell us what the answer to the communication problem should be. So this means that if we are able to get such a reduction, then it would give us a lower bound to how much space does the streaming algorithm need. So let's see an example. Let's reduce disjointness to computing the second moment. So what is the disjointness problem? We have, let's think of it as a vector or a set of elements of size n is Alice's input, and the vector of length n or a set of elements of size n as the input of Bob, and they need to tell if those two sets are disjoint or not. If they're binary vectors, they have a common one or not. And those two things are equivalent. And we know that this communication problem has a lower bound, which is simply sending the entire input. So you cannot solve disjointness without revealing more or less your entire input to the other player, maybe up to constants. But you need roughly, if the input is n bits long, I need to send the order of n bits to the second player. So what is going to be exactly the size of things we are going to reduce? So we are going to reduce disjointness of vectors of length 1 over epsilon to the problem of 1 plus minus epsilon estimation of f2. And what is going to be the reduction? The reduction is going to be quite straightforward. So Alice simply is going to write in her half of the stream her input, all of the elements in her set of the disjointness problem, and Bob is going to write in his half of the stream his input, his set for the disjointness problem. And now we're going to make the following simple observation. What is the second moment of this entire stream? So every element that appeared only in Alice's part or only in Bob's part is going to contribute 1 to the second moment, right? Because it is an element that appears of frequency 1. But an element that appeared both in Alice's input and in Bob's input, its frequency is going to be 2, meaning that its contribution to the second moment is now 2 squared. This is 4, which is more than 1 plus 1. Right, so this means that the entire F2 of the stream is going to be the size of Alice's set plus the size of Bob's set plus twice the size of the intersection between the sets. And we didn't really care about this being the second moment here. All we cared about is that 2 to the power of k minus 1 to the power of k minus 1 to the power of k was not exactly the same as not 0. Right? So any moment besides the first moment, besides approximate counting, would this lower bound would work for. Good. So this means that from the second moment, if we approximate it well enough, if we know it exactly, we could just say what is the size of the intersection of their sets. And in particular, whether or not they were disjoint. So how good of an estimation do we need to be able to say if the intersection was of size 0 or if it was not of size 0, if it was of size 1, for example? So if we said that we started with sets of size 1 over epsilon, then we just need to have an epsilon approximation to be able to distinguish between no intersection and intersection of size 1. So this means that if we have 1 plus minus epsilon approximation for F2, we can also solve this jointness for vectors of size 1 over epsilon, which in turn means that we need at least 1 over epsilon space for the F2 streaming problem because of this exact reduction we've just seen. And the same recipe, the very same recipe, would work to get better and better bounds. And as we said, it would also work for getting bounds for other moments and for other streaming problems. So for example, if instead of the disjointness communication problem, we would have started from the equality problem, then with a little massage of what we have just seen, we would be able to get a log n space lower bound for F2. So those two bounds are extremely easy to get. Log n plus 1 over epsilon squared. 1 over epsilon, so without the square form. To get the 1 over epsilon squared instead of 1 over epsilon, we still needed exactly the same recipe, but a slightly more complicated communication problem. So here David Woodruff came up with something called the gap Hamming distance problem. So this is just a slightly more complicated communication problem, but then the reduction is exactly the same. So we just have a more complicated communication problem, maybe a more hard to prove lower bound in the communication settings for this problem. But once we have the communication problem and the lower bound for the communication problem, this was exactly the same reduction. Just put it in the two halves of the stream, and this would tell us that we need at least 1 over epsilon squared space. Good. So this very same recipe was all we needed to get the previous lower bounds. And when you talked about other moments, things needed to get slightly more complicated, but not by a lot. So they could get slightly more complicated by maybe not having 2 players, but T players. Or maybe by having slightly more complicated bounds in the communication settings. But all of them looked like reductions from communication problems to the streaming problem. Good. And for some reason, people didn't manage to find the right communication problem that would give us log n times 1 over epsilon squared. And then something like 5 years ago, Raj Jayaram and David Woodruff realized why. So what they showed is that if we forgot about the streaming model for a second and just tried in the communication model to solve the problem of computing or estimating the second moment, meaning that I would give Alice half of the elements in my stream, I would give Bob half of the elements in my stream, and I would ask them to compute the second moment, or even if I would do it with a few players, then actually they wouldn't need a lot of communication to do that. They would only need log n plus 1 over epsilon squared communication to do that, matching our current lower bounds. This means in particular that this type of reductions, as long as they stay with this like very same recipe, they cannot yield better lower bounds. Right? Because if I add a communication problem that I could reduce to computing the second moment of a stream, and this would be supposed to give me a higher lower bound, it wouldn't make any sense because I could solve the communication problem by just solving in the communication world the computation of the second moment, and from that the players would be able to deduce the answer. So this means that those simple type of reductions from communication to streaming wouldn't be enough to break out of the current best lower bounds, which is sad because this is what we did so far. So the question is, what can we do beyond that? So now let me try to sketch our idea. How do we break from just this recipe of communication to streaming? So the idea we're going to use is the following. So something people used a lot in the communication settings to prove lower bounds is something, and this is used in many other settings as well, is something called direct sum theorems, showing that if I have many independent copies of some problem, then solving all of them together should be as hard as solving each of them individually. So we would want to have a type of a direct sum theorem, but in a very weird manner. So what do I mean by that? What we would want to do is to still start with some communication problems, and we would have a collection of not one communication problem, but many communication problems. And somehow we would embed all of them in our stream. And we would want to show that if the streaming algorithm succeeds, then it solved each of those communication problems and it needed to work as hard as if it solved each of them independently. But the weird thing is going to be that those problems are not going to be independent. They're going to be actually very, very much dependent. So in particular, this wouldn't give us a communication problem with a higher lower bound. Because if I would try to solve it in the communication setting, I could solve it with less communication because I would have many instances of a problem and all of them would be dependent with each other, so I wouldn't really need to solve each of them individually. But we are going to somehow show that if we are doing this direct sum at the level of the stream and not at the level of the communication problem, then because the streaming algorithm is more restricted, it would somehow miss that the instances are dependent. And we can trick the streaming algorithm into thinking that it solves independent instances. So let's try to say slightly more than this. To be able to say slightly more than this, I need to say something else about how many of the communication lower bounds are achieved. And there is something called information complexity that we use to achieve them. Which means that instead of asking ourselves how many bits does Alice need to send Bob for this communication problem to be solved, we are going to ask how much information should be between the message that Alice sends and the input that Alice has. So for example, sending things like random bits or sending things like a hash function, this has no information about the input. And then we can also not really hope that those things would have a direct sum, that they would sum up. Because maybe random bits can be used by all of the instances at the same time. But something that is information about the specific input Alice has, this has more chance of having a direct sum theorem. This is why this notion of information instead of how many bits she sends is more useful for many of those lower bounds. But to be able to speak formally about information, we need a distribution. So information is something that we define for a distribution. So when I ask how much information is there between the message Alice sends and the input that Alice has, this is with respect to a certain distribution of inputs for Alice. But one thing I want to point out is that this distribution is not necessarily a hard distribution for the problem. So what we are going to do whenever we are using information complexity in these lower bounds is showing that if there is an algorithm that succeeds in the worst case, that succeeds on every input, then on this distribution, it has to have a lot of information between the message sent and the input that Alice had. But again, this doesn't mean that this distribution was necessarily hard. For example, it could be that this distribution would just be, I don't know, if we are trying to solve equality, then maybe any protocol that succeeds on every input must have a lot of information when Alice has a random input in her side, even though the random input for equality is very easy to solve. They are not equal, right, with a very high probability. But nonetheless, if for a random input Alice sends very few bits, then it has no chance of succeeding for every pair of inputs. Right, so just keep in mind that a distribution on which we have a lot of information doesn't mean hard distribution. Good. So the first step in our reduction is constructing a much more flexible lower bound for in the communication sense that would still just recover the same lower bound that we had before of 1 over epsilon squared. So what do I mean by flexible? What flexibility do I want? So I want flexibility in a few ways. So one thing I want is that now I wouldn't have two players, I would have t players, such that each of them would have an input of size n over t. So the total size of the problem always remains n. I just can partition the input between as many players as I want. This is one variability or flexibility that I am going to use. The second thing I want is that there will be a 1 over epsilon squared lower bound for this communication problem. But what do I mean by that exactly? What I mean is that to solve whichever communication problem I am defining between those t players, then the average information that a player has to say about their input is something like 1 over epsilon squared. What do I mean by that? What I mean is that if I have more players, then each of them would need to say something like 1 over epsilon squared, or at least in average, each of them would need to say something like 1 over epsilon squared bits of information about their input. So if I have more players, then in total, the amount of communication they need is larger. So the average always remains 1 over epsilon squared. And as before, this would, one other thing, not only that this requires a lot of information, it requires a lot of information on the uniform input distribution. So for this problem, even if my input is just giving n over t random elements to each of the t players, then on this distribution, there needs to be that much information between their messages and the inputs. And finally, as we needed in all of the reductions, this reduces to computing F2. So the simple reduction or similar reduction to the simple reduction from before would still work. It would still be true that if I can compute the F2 of the stream and I partition it between the players, then the result would tell me the answer to my weird communication problem. Okay, so let's see some drawing. In the reductions we have seen so far, we had two players. Each of them just placed their input in one half of the stream. And we said that to get a communication problem, the first player needs to send the memory at this pink arrow point to the second player. This was the communication protocol, the way we got the communication protocol from the streaming protocol. Just needed to send the memory from this point from the first player to the second player. So what will happen with t players? A very similar reduction. So now we would partition the stream into t parts, not only into two parts. Each part would encode the input of a different player. And now the way the reduction would work is that the first player would simulate their part of the stream and send the memory here to the second player. The second player picks up from this memory. It can start simulating the stream on his part of the stream, the part that is an encoding of his input, then send it to the third player. The memory at this point, it can send to the third player, and so on. And just for symmetry, we are going to imagine as if the last player is also sending something at the end of his turn. but the last player is just going to send the output or something, right? It is not and is no longer communicating with anyone. Good. And then the lower bound would be the lower bound for the sum of the memory in all of those pink arrows. But fortunately for us, we said that the average remains 1 over epsilon squared. So if the sum of the memories in the pink arrows over the number of pink arrows is 1 over epsilon squared, then we just recover the same 1 over epsilon squared bound as we had before. Good. One extra observation we are going to need is that in this reduction, the same type of reduction we've seen before, we could add gaps between the players. What do I mean by gaps? I could have parts of the stream that do not belong to any player. And in those parts of the stream, I would just have completely random elements independently. So some parts of the stream, the parts that are colored, encode the input of one of the players, but the gray parts, they just have random elements in them. And assume my universe of elements is large enough. Why doesn't that matter? It doesn't matter because the random elements I am adding, if I'm drawing them uniformly from a large enough universe, each of them will be a brand new element that never appears more than once. So each of those gray elements is just going to contribute 1 to the second frequency moment. So in the very end, we can just subtract the amount of gray elements we add. So this is now a randomized reduction from the communication problem to the streaming problem, but it works exactly the same as before. We just subtract the sizes of these gray areas in the end, and nothing changes. But this also means that the point in which each player finishes and the next player picks up, it doesn't have to be immediately after the part that encodes his own input. It can be at any place within this gap. What do I mean by that? I mean that the first player can look at the encoding of its own input, simulate the stream up to here, but any player is able to draw random elements. So it can draw this gray element and this gray element and this gray element just uniformly at random and get up to this point, and only then send the memory to the second player. And from here, the second player can pick up, right? The second player can draw those gray random elements, and now when it needs its input, it has its input. And after it finishes, it can turn it to the next player and so on. So the only important thing is that the part that actually encodes the input of a player would be fully within the part that this player simulates. But the gray elements, we don't care which element simulates them. Each of them is fine. So what did we deduce? So what we deduced using this reduction and the fact that we have a lower bound that is information-based, and we said that it is a lower bound that is information-based for the distribution of uniformly chosen random elements, what we deduce from that is that if I look at a stream of elements that is completely random, all of it is random, both the gray parts and the parts that are players' inputs, and I pick any place within those gray gaps for my arrows, then the information between the memory at the arrow points and the parts of this random stream that are colored that were corresponding to players' inputs must be at least this 1 over epsilon squared in average over the number of arrows. So this is now just a completely random stream, right? Because we said that for any placing of inputs in the colored parts, this reduction ends with us solving the problem. And then the information lower bound we have means that even if we choose as the distribution of inputs the uniform distribution, then we would have a lot of information between the messages and the inputs. So this means that in a completely uniformly random stream, those locations would know something about which elements were in the colored parts, which random elements were drawn to be put into those colored parts. And now the second observation we need to make is that if we ended up with a completely uniform random stream, then it didn't matter which number of players we started for, right? Because we added those we added those gaps, we added some random elements at some points, we switched the input distribution to the streaming problem to also be the uniform distribution of random elements. This means that I end up with exactly the same distribution of a completely random stream, regardless of how many players I started with. Which means that the very same stream, the same distribution of a completely uniformly drawn random stream, this statement would be true for it regardless of how many players I'm partitioning it to. So for any t, if I would partition it to t parts and draw those t-colored parts and pick places for the arrows, this thing would be true. So what can we do with it? So let's imagine that I'm trying to play the very same game, but not only with a specific number of t players, but with powers of 2. So I think of it as if my stream encodes the problem for 2 players, and it encodes the problem for 4 players, and it encodes the problem for 8 players, and so on. And the size of those gaps that I'm adding between the players would always be roughly the same or by a constant larger than the size of the player inputs. So I still want to use a constant fraction of the stream for the player inputs to not change n or anything. So those gaps are of the same size more or less as the actual player sizes. So the very same distribution of streams, I could think of it either as something that encodes this type of problem with 2 players, or this type of problem with 4 players, or this type of problems with 8 players, and so on. And now I would notice that all of those instances of what I view as different problems, at some points do not intersect each other. At some points there is only one actual player, and in the other levels, in the other instances, I just see random elements. But in certain places, they do intersect each other. Actually, in many places, right? Each 2 of them intersect each other in a constant fraction of places. But it turns out that because we took those exponentially growing distances between the players, between one level and the next one, that for a random index, for an average index, if you just look at the last player, the part that represents the input of the last player before this index in each of the levels, then many of them are going to be completely disjoint. Why? Because the gap here is long enough that it is likely that the last player here falls completely within this gap. And the gap here is long enough that it is likely that this player falls completely within this path. So not all of them will be disjoint, but with good probability, something like half of them will be disjoint, or a quarter of them will be disjoint. But a constant fraction of the levels locally, if I just take a random index and look at the last player in each level, locally, a constant fraction of the level appears disjoint. And I'm not going to explain technically why is that enough, but it turns out that this is enough, because this means that from the point of view of this specific index, which holds the entire memory that should be enough to solve the problem for all of the levels, not all log n levels, but something like half of the log n levels appear completely independent. So this specific index, the memory it has nothing to do but to have separated memory for each of those log n over 2 levels. Because even though globally they intersect each other, from this index's point of view, they are disjoint, many of the levels. And for another index, several others are disjoint. So locally, you need to remember something about order of magnitude log n levels that appear independent to you. So an average index thinks that it sees roughly log n independent levels, and for each of them, it needs to know 1 over epsilon squared information, again on average, because this was the lower bound for each particular level. So from the point of view of an average index, it needs log n times 1 over epsilon squared information about all of those levels together. And it turns out that you can actually turn this into a global direct sum. So this fact that locally things look independent is enough to show that at least in some point you need that much memory. So this is the way we get this log something over epsilon squared lower bound. So what we have is exactly that. So we have log of epsilon squared n instances at the same time, and each of them would give us 1 over epsilon squared lower bound. Good. I think that I am not that much beyond time, right? Probably, and still within the hour. So yeah, thank you very much, everyone, for listening. I hope that not having questions during the talk was out of politeness or something, not because everyone lost me. But yes, questions after the talk or after the recording would be very good to get as well.
Okay. Please, thanks, Or, for the talk. Actually, I just have maybe one quick question. Can you say a word or two about the upper bound, that how you like change?
Good. Good. Very good question. It is such a good question that I have an extra slide about it, just hiding immediately after the current one. So actually, the upper bound is extremely simple. It doesn't take any grandiose ideas. So let's remember what was the AMS bound. We had this simple counter thing, and we ran it in parallel 1 over epsilon squared times independently. So all we are going to do is to make those 1 over epsilon squared runs disjoint, meaning that I will have another function that maps each element to one of the 1 over epsilon squared instances. And then instead of whenever I see an element to update the counters in all of them, I would have only one index in which I need to update the counter. So each element I am seeing is going to update only one of the counters. And it turns out that this is good enough to reduce the variance. It doesn't matter that much because I still have an average of many things. The fact that those things are slightly smaller, that I partitioned it instead of duplicating it, it doesn't change the variance by much. But what does it change? It changes the fact that now in each of these 1 over epsilon squared buckets, I no longer have n elements that I am running a counter on, but only epsilon squared times n elements. Right? Because I had n elements in total and I partitioned them to 1 over epsilon squared things. So now for the counter, I only need epsilon log of epsilon squared n bits and not log n bits. And you need to do something about the functions, but it's not nothing too crazy.
I see. But do you have like an additive log n bound for the hash functions? I mean, or it
Good.
doesn't
So
matter at that point for the epsilon?
good. So the observation we are making is that if the elements are partitioned between the different buckets, then actually this mu function that gives a random sign for each element, we only need one of those. We don't need 1 over epsilon squared of those, right? Because each element only appears in one of them. So it's enough to draw one function that would assign a sign to each element and one function that would partition the elements, that would tell each element which index of bucket it should fall into. So we only have two functions. So for the counters, you would have 1 over epsilon squared times log epsilon squared n, and then you have an additive log n for the two global functions you maintain. But you no longer need a function within each bucket.
Okay. Or I guess, are there any other questions? Um,
Hi, I have a question. Okay. So basically, I think your technique works because you use multi-party communication model instead of two-party model, right? Because if you use multi-party communication model, basically it's possible to say that you will use more bits to compute something, then it's possible to improve your load bound, right?
Yeah, so previous lower bounds did use multi-party communication, so you could use that. The way that we are using multi-party communication is a bit weird, is that we are using multi-party communication with different number of players in each level to make sure that we are constructing something that is harder for the streaming algorithm than it would have been as a communication problem. Why? because now there isn't just very few places in which you can separate the different players. Because there is one place in which you separate the two players of the communication problem with two players, and another places in which you separate them for several players, and another place for another number of players, and so on. So you have this weird situation in which each index is in a certain player in the first instance, and the different player in the second instance, and the different players in the third instance. So each index is in some weird positioning among all different instances. So it's not only that you have many players, it's the fact that now a streaming index corresponds to something weird across all instances and not just to one player in one communication instance.
Okay, thank you.
I think Raj is also asking in the chat whether or not the lower bound can be
Well, I
in.
was just saying, I think the previous multi-party stuff was Blackboard, right? But Blackboard here has the same issue that, you can simulate a low diameter communication protocol, so it can't be Blackboard.
Good. Yes. So yeah, I mean, we are using the fact that what happens is not a blackboard thing because I mean, if we have n players like in the streaming instance, having a blackboard would just mean that they can all write
Right.
their inputs entirely. Um, yes, but it seems like using the fact that you're in a message passing model and not in a blackboard model to get very good lower bounds for communication in like weird communication graphs is not very easy. We're not very good
Yeah.
with doing that.
Thanks. Yeah, very nice talk. Have to run now, but yeah, thanks again.
Thanks. Thank you.
Okay, so I'll go ahead and stop the recording.